Okay, so there's a question of how would it work if we threw in additional splines. Basically, it works. It would work the same way, and it's just we would throw in basically another predictor, right? So this is at x equal to 0. We have across the board we're going to have 0 here, and then at x equal to 1 we've got 1 1 1. Here, I'm going to just do the cubed part, and then we get 2, 4, 8, and 3, 9, 27, and so this becomes 16, 25, 36, 49, 64, and then, I don't know my cubes, what is this, 64, 125, 216, and 343, and 512, is that right? Okay, and then at xi equal to 4, basically, this is going to be 0 all the way until at 4, then we just start 1, 8, 27, 64, so on and so forth. And then with xi equal to 7, everything's going to be a 0 until we get to this part, and this continues to 1, 8, 27, 64, 125, 216, 343, so on and so forth. Okay, so you just have another element or another term to throw into your linear model, and you would just ask R. You could say y is, you would do lm y as a function of x plus x squared plus x cubed plus h of x with 4 and h of x with 7, and it would try to fit some kind of cubic basis spline there. Okay, so it's just imagine this column x3, x cubed, but shifted to where the spline begins, and then you're just throwing that term into the line. Okay, so where do we try to how many knots do we need? How many and where should the knots be located? Basically, the knot gives it a certain amount of flexibility, right? So the knot increases the amount of flexibility in that zone. So if you see, when you're looking at the function, you might say, well, we should put a knot around here because this is where the shape seems to be kind of the most flexible. That's kind of where you can do it. And we can also use kind of cross-validation between the degrees of freedom that we're using and what we're fitting. Okay, and you can kind of if you plot the degrees of freedom of the spline versus the kind of the cross-validation error, you can get an idea of what is the appropriate degrees of freedom to use. Okay, your degrees of freedom again is the number of knots for a cubic spline. It's number of knots plus 4, because you've got the 3 coefficients plus your constant. So those are your 4 in addition to however many knots you have. So if you have 2 knots, you've got 1, 2, 3, 4, 5 plus the intercept term to estimate. Another method for kind of fitting some kind of smooth function is by using a smoothing spline. Okay. Okay. And so we might say that we want a function, just pick some arbitrary function that minimizes the residual sum of squares, right? So maybe okay. And so we could say, you know, so we'll say the residual sum of squares is going to be the difference between y and the function when we plug in, you know, our value x sub I, okay? And this is going to be the total between, you know, each actual value yi minus its prediction. If we put no constraints on what the function g can be, then using this as our kind of our guiding rule, we'll produce functions that are, you know, probably way too wiggly, and g of x, this RSS will be minimized when g of x fits the data perfectly, okay? If we put no constraints on what the function can be, and we use minimizing then g of x will try to fit the data perfectly. And so far we haven't talked at all about how g of x would be calculated, but you know, g of x, if this is our only guide, this is going to fit the data, try to fit the data perfectly, and will thus overfit, be too wiggly, and will overfit. So what can we do to kind of address this? All right. So again, we haven't even mentioned the form of g of x, but to address this, we can say, you know what, we're going to introduce kind of a penalty for how wiggly g of x is, okay, or how smooth or how rough g of x is, okay. So instead of minimizing RSS, we can include a kind of a penalty term. And so this is a common thing, is we'll say we want to minimize this thing, but don't go overboard because we're going to introduce a penalty for making it too complicated, right? So instead of minimizing RSS alone, minimize basically RSS plus a roughness penalty, okay? And this will basically look something like, so you have your RSS term, y sub I minus g of x sub I, plus lambda times the integral of the second derivative of g. Okay, so this part, this is the penalty term. related to the second derivative. Okay, so the second derivative kind of gives us an idea of how smooth the function is. And so if this is, if the function is extremely rough, then the integral of the second derivative will be quite large, right? And this lambda over here is kind of a tuning parameter. So how important is it that it is smooth? Okay, so this is a tuning parameter. How important is it that we smooth things out? Well, that's going to be controlled by lambda. So, if lambda were equal to 0, then there's no penalty for having a super rough line. And then if you have lambda turned up, to infinity, then it's going to force pretty much like a quadratic shape. Yes, question.
So it's that going to be a definite interval?
I guess, yeah. It would be over the span of the data. Yeah. But yeah, so this is kind of just more so kind of the notion that we're going for. And so if just kind of to illustrate, if this is what we have, and we've got some so if there's no penalty for I don't know. It's going to try to fit the data. Fit the data perfectly, and you're going to get something kind of at the expense of something like this, right? So this is no penalty for being too wiggly. And on the other hand, if you have lambda cranked up really high, then it has to be super smooth, and you're going to get some probably like a quadratic looking thing or something. And you probably want some kind of happy medium. I don't know what exactly that means, but I don't know, something, right? This is probably lambda is good. Here, lambda is too small. And then over here, we would have lambda too large. Okay, and again, we haven't even talked about, the form that of G that we would need to use, right? So this is just kind of some arbitrary function G. This is for function G of X. So, oftentimes to choose the lambda is chosen often by cross-validation, okay? Okay, and then the kind of the last topic. So this was all about kind of fitting splines to our data. And one more thing that we might want to try to do is perform local regression. Okay. So this is often called Lois, sometimes with the W for like weighted, but it's like the same. This is basically local regression. And this is basically it's a nonparametric method. And what it is effectively you can kind of think of it as eyeballing a smooth curve through the data. Okay, so this is, you know, a nonparametric method. So we don't, we're not going to get like a closed form, you know, y is equal to this equation of x. Okay, we get basically just a drawn curve, you know, set of coordinates that we use, and it's kind of, you can think of it as you know, a recipe to eyeball a smooth curve through the data. Okay, and so we can think of this as kind of, you know, it's similar. It's related to the idea, similar to the idea of a running mean, not a weighted, running mean. Okay, and so let's say you've got some data here. Okay, and with a running mean, for a running mean, basically you create some kind of window of values, a window of how many values we're going to average together. So maybe I will have a value of a set of, I'm going to average 1, 2, 3, 4, 5. I'll take these 5 values, okay? And this is kind of my, my first window. And I would say, you know, what is the mean of these 5 values? The mean here, 1, 2, 3, 4, 5, is going to be somewhere like, I don't know, right here, okay? So I'm going to just draw a line kind of right here. So if I took these 5, well, I don't know, maybe it's lower than that. Something like this, right? Okay. So, because we're looking in terms of y, just on the y-axis, this is where we go, okay? So if I took the average of these 5 values, maybe I get this, right? And then if we move along over to the next set of 5 values, now I'm right here. I'm going from here to here, okay? And so I look at 1, 2, 3, 4, 5, and what is the mean of these 5 values? A little bit higher, maybe like right there. Is that okay? And then I move on, and now I'm going to look at these 5 values, and now it's going to be right there or something. Or maybe it's hard to draw. Okay, and so if we so if I'm kind of averaging where I've been for in bright yellow, we'll plot the center of my values here. So it goes right here to right here to right here. So now my weighted running mean, you can't see that. Goes through these points here, okay? So I'm doing basically I'm taking kind of a window of values and I'm averaging those values there. Includes some of the values above x, values above and below x. Okay, and then you just take the mean of those values. Does that okay, is that all right? So for a running mean, we're just taking, we say, for these 5 values between here and here, what's the average of these 5 values? Then we move to we shift the window a little bit. What's the average of these 5 values? We shift the window. What's the average of these 5 values? And then we just calculate a running mean for kind of as that window slides along. Okay, and so every time an x drops out and a new x drops in, our running mean changes. Local regression, we basically do the same thing, except the running mean has just, maybe we have we put the x value in the middle and we take the 2 values lower and the 2 values above it, okay? Or you might say, I want the 6 values below and the 6 values above, and that's going to kind of make the running mean a lot more, smooth in that regard, okay? Or it doesn't change values as much, okay? With local regression, we do something similar, except rather than just saying the 6 values below and the 6 values above, or the 2 values below and the 2 values above, we put weights on the values close to the x, and we reduce the weights that are far away. Okay, so maybe it ends up being you factor in the 6 values below and the 6 values above, but the one that is closest to x, those have a weight of 1, and then the ones that are 2 measurements away from x, maybe those have a weight of 0.8. And then the ones that are further away have a weight of 0.6, then 0.4, and 0.2 down to 0. Okay, and so now we have the values closer to our location x. Those values factor more into the average, and the other values factor less. Okay, so with local regression, we weigh the values near x to be high, and the values far from x to be lower. Okay, and then and rather than just averaging them, we would fit kind of a weighted least squares model for that kind of window of data. Okay, so rather than just averaging, have you guys covered weighted least squares regression? No? Okay, so with least squares regression, the guiding force is you are trying to minimize the squares of the residuals. Right? With weighted least squares regression, all squared residuals are not equal. Okay, so with weighted least squares regression, you have some set of weights that say these residuals are way more important than these other residuals. Therefore, we want to focus our energies minimizing these residuals, and if these other residuals are big, that's okay. All right, that's all. All right, so weighted least squares regression just says rather than trying to minimize all the squared residuals, we're going to try to minimize the squared residuals, but some residuals are more important than others, and that importance is determined by the weights. Okay, we no longer have, so again, the disadvantage here though is we will not have a functional form of y and x. Okay. Instead, we're just able to predict a y for a particular x. Okay, we are just able to predict y for a particular. Okay, I mean, I guess if you predict a bunch of y's for all of the x's, that could be a functional form, but it's not a nice functional form. It's a function based on the data that goes in and all of the weighting that goes in. Okay, so that allows us to kind of fit local regression models there, and okay, and then we just combine all of this into the generalized additive model. Okay, so with the generalized additive model, all we do is so if we have, so just let's just step back. So with multiple linear regression, we have, yi equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 all the way up to beta sub p xi sub p plus epsilon sub I. Okay, with the generalized with the GAM we have beta 0 plus the function xi1, some functional form of xi1, and this could be, polynomial, or smoothing, cubic basis spline, or Lois regression, or some other form, okay, some function of x1, right? Okay, and then we have some other function f2 of x sub I2 all the way up to some pth function of x sub I p. Okay, or so each of these functions that we're adding, they're just some form. It could be a nice polynomial or linear form, but it could also be a smoothing spline or something. Okay, and we just add the results of those together to get our prediction. So the general form would be B0 plus the sum of j sub 1 to p of f sub j of xi sub j plus epsilon sub I. Okay, and so we'll take a look at a couple some data sets here, and we'll try to explain maybe we'll just take a look at what we can fit. Okay. Okay, so let's take a look. Okay, so I'm going to start off with the this first data set, which is the time of the 1500 men's track and field event at the at different Olympics. Okay, so this is we're going to look at kind of the Handbook of Statistical Analysis using R, and we'll first look at this data set men 1500M, which is the men's 1500 meter track and field race, and we're going to look at kind of the time it took. Okay, and so far, if we look at this data, okay, all we have is year, venue, winner, country, and time. So really, we'll just look at the relationship between year and time. So if I plot this, it looks like this. Okay, so we got this kind of thing, and then we kind of have this a little bit of an outlier there. So I think it makes sense to remove the this first outlier, because this really doesn't fit in with the rest of the data. So we'll go ahead and we'll go ahead and remove that one outlier, okay, which was the year 1896. I think that was the first one the competitiveness wasn't as great. Okay, so we'll we can plot this. Okay, so this looks better, and we can just fit a linear model between winning time and the year. Okay, and if I plot that line, it looks like that. And let's just do color equals blue. Line width equals 2. Let's do that. Okay, so this is just fitting a linear model, and then so we can see what are the predicted times for 2008 and 2012. And so we would just take our linear model, and then we would just throw in, prediction. Oops, did that not work? No. Okay. And it says, we would predict times of 208 and 206, okay, and that's what we have. Okay, maybe we want to fit a quadratic model. That's easy. All we do is we just fit year plus year squared. Okay, and we can do that. This. Okay, and so this is kind of a quadratic model, and then if we do this, we can see what kind of prediction do we get, and we fit 214 or something. So again, with the quadratic model, eventually the predicted times will start curving up, which that's kind of the warning against doing extrapolating on whatever model you have, right? And with the regular linear model, if we extrapolate, then eventually we'll get a time of 0, which would not make sense either. Okay, so here we can do Lois. Okay, so Lois, you just fit in, punch in x and y. Okay, and you can see with Lois, all it does is it does something to kind of just make a prediction between x and y. So we don't have a nice linear form with coefficients relating x and y. We just say, okay, you gave me an x and you gave me a y. Okay, this is now what I'm going to predict for x and y based on these two things. So this would be what I have here, and so here I'll plot my data here, and let's do color equals blue. 2. Okay, and so Lois regression, again, all that does is it just tries to fit a smooth line to the data by weighting certain values, heavier versus other values there. Okay, and so this would be our Lois fit. Okay. And with Lois, we would have a hard time kind of extrapolating, because we really only can go. All we can do is just make predictions for where we do have actual data points. Okay, with we can fit a cubic regression spline with the function GAM. Okay, so GAM allows us to fit cubic regression splines. I think yeah, we got to load up library GAM here. Okay. try this again. If we want, we can fit a where to go? Cubic regression spline. Okay, so we're going to just say gamma is a fit between y, and then here this function s fits a spline. Okay, a smoothing spline in a gam formula, and your options for the BS for the basis is that, you know, here we want cubic regression is the option here. So we're going to fit that. So we've got this, and then let me do color equals green, and line width equals 2 also. Used argument basis spline. Okay, this is not. Sorry. Oh, maybe I just do BS. Okay, sorry. I'm gonna have to modify this. 3 equals 3. This will do. Okay, so I don't know if you can really see the difference here. All right, so I guess for a basis spline, we don't say S, we say BS based on X with a degree of 3, and it fits kind of a cubic thing, and you can kind of see the difference between the Lois fit and the cubic regression fit, and it's hard to you know, it's a little, you know, the difference is down here, and this is where it's really hard to evaluate because the future hasn't happened yet, right? So, you know, as far as predicting the future, we really don't know what's going to happen. So, you know, either of these, they seem like they do a good job of fitting the past data, right? But a lot of times we want to predict the future, but that's always just kind of impossible. Okay. We can also take a look at another set of data. This is some wage data, and here we're going to use the textbook ISLR, and we want to see you know, what kind of predictors go into determining someone's wages. So we got, you know, reported back the wage of you know, a whole bunch of different people, and we collected information on their age and all sorts of stuff here. So, you know, if I just do a plot between, let me attach. Capital wage here. Okay, it says Mid-Atlantic wage data. It says wage and other data for a group of 3,000 male workers in the Mid-Atlantic region. Okay, and we have just different information, such as, you know, the year it was collected, the age of the worker, marital status, the race, education, the region, job class being industrial or information, you know, their health, and, you know, and we can look at the log wage, the log of the worker's wage, and the wage itself, okay? But it looks crazy, right? Because we've got all sorts of, so if I just plot wage against age, this is what it looks like. It's just, there's tons of data points, right? So we've got, you know, wages anywhere from here, you know, there's a huge, you know, how can you fit something like this, right? And then we got people making lots of money also. So, you know, what can we do? So if I fit, I can fit just if I just do a regular old linear model, this is going to be kind of a terrible fit. And, if I do this, okay, this is not a very good fit at all, right? So we can try fitting a fourth order polynomial, and we can say fit wage for poly, okay, and did I mess something up here? So this time we will fit. Cole is not a graphic programmer. Okay, so we're gonna try to fit a fourth order polynomial here, and then we can take a look at the coefficients here. If you're not familiar with poly, so poly just turns this into kind of first, second, third, and fourth degree polynomials. Raw equals true is kind of what we would expect if we did x squared, x cubed, and x to the fourth. If you just do poly, it doesn't do that. It does something similar, but they're orthogonal to the constant polynomial. But anyway, you can do this, and you can fit it, right? And if we want to see what this looks like, we can. So the age limits is the range of our age data. So we have data going from 18 years old to 80 years old, and then we're going to we're going to use our fitted polynomial, and we're going to create a prediction there. Okay, we're going to say predict new age to what we have. We get all of our we get this when you do predict, you can also get the standard error. Okay, so SE is include the standard error of our prediction, and then we can calculate standard error bands by going up or down 2 standard errors, 1.96 or whatever you want. And so in this case, here's our plot of the wage data, and then we're going to fit the fourth degree polynomial to it. This is what we have on this side. So this is all the wage data we have, and then fitting a fourth degree polynomial looks like that on that side. And then on the other side, we can okay, and over here, we just fit a whole bunch of, here we added into our plot, we added standard error bands, and so you can see in the middle, the standard errors are small, but then as we get fewer and fewer data points to make our predictions out here, the standard errors grow in this region. So we're not quite sure how the data actually goes out there. We also just fit a bunch of other possibilities. Okay, so linear model, quadratic, cubic, order 4 and order 5, and we can run the command ANOVA to kind of just see the difference in terms of how many, whether it's worth having the additional degrees of freedom, right? So if we fit the difference between first and second order, we reduce the number of degrees of freedom, but it has a significant impact. Okay, going further up, at what point do we make the difference? And so going from third to fourth, we have a p-value of around 0.05, and then fifth order, p-value around 0.37. So it seems like, okay, it makes sense to go to the fourth degree. Okay, maybe even the third degree. Okay, and so we kind of fit all of this, and this is a logistic model. I don't think we want to actually do that, but you can further going into this. Let's see. Okay, so yeah, this is a logistic model. We haven't covered that, so I'm going to just skip this. This was I'm taking the code from the textbook, so we'll skip that. Let me see, standard error bands on the logistic there. We don't want that. Okay. All right, so this is fitting a fourth order polynomial. Let me change my MF row. Instead of fitting a polynomial, we might use some kind of basis spline, right? And so so here we might create we'll use library splines here, and we can fit a basis spline using age with knots placed at 25, 40, and 60. So if kind of looking at this, it seems like we would start. Maybe there's a kind of a shift around those areas, 25, 40, and 60. Maybe, it's hard to say. And so we can do this. We'll create our fit there using our basis spline. And then so now our predictions, we use the prediction function again, and we'll say predict using the model fit, using our new data. New data again is just the grid, age grid being kind of all of the values that we calculated from 18 to 80. So this is just the values 18 to 80 with standard errors. Okay, so here again is our data, and we're going to fit in our prediction here. So this is what it looks like using some basis splines here. Okay, the default value for basis spline is to have a third order fit here. Okay, so this is our cubic basis splines. It looks, so the difference, I don't know, we'll make this bigger. So this is our cubic basis spline, and this is our fourth order polynomial. Okay, so they're both giving us similar results, but the cubic basis spline, maybe has a slightly different shape at certain points here. Okay, and the behavior and the tails are probably the most at the edges are going to be what's most different. Okay, if we wanted to, we can see the results of our basis splines here. We gave it the knots 25, 40, and 60. We can say we could just say we want 6 degrees of freedom here, and if we asked, you know, where to place the knots. Okay, so here when we did this, we placed the knots at 25, 40, and 60. If we just said do it with 6 degrees of freedom, and it's going to kind of use its own determination as to, you know, maybe where the knots should go. It's going to just kind of place them at uniform quantile locations. So in this case, because it's fitting cubic order, and you know, it's going to kind of place three knots here, and that, so it splits it at 25, 50, 70. If I said give me 4 locations, then it's going to split them up at 20, 40, 60, and 80, and things like that. Okay, so if you didn't want to specify the locations of the knots yourself, you can just say specify the degrees of freedom of your basis spline, and then and it will spread out the knots evenly. We have the other option is the natural spline, and we also have the smoothing spline. You know, we didn't get super into the details of the natural spline or the smoothing spline. Pretty much they're very similar and related to basis splines. Okay, with the basis splines we had I was able to explain how those basis spline functions come in with the h and the xi. With the natural splines and the smoothing splines, it's a little bit more complex, but the net result at the end is going to be fairly similar. So I'll just show you what this might look like. Okay, so if we fit a natural spline, we can create our predictions, and we can add the natural spline there. Okay, and so again, the difference here is that with a cubic basis spline, we are still at some degree fitting cubic functions to the data, and so you'll have at a certain point a little bit like the trajectory of a cubic function. Okay, and with a natural spline, you don't have that there. Okay, so yeah, natural. How does a natural cubic spline go? Okay, so that's for a natural spline, and then also for a smoothing spline. These are just different variants of kind of these smoothing things. Okay, so we'll create a smoothing spline here. We have smoothing spline with 16 degrees of freedom, and fit to smoothing spline here. CV equals true means determine the degrees of freedom using cross-validation, and we can kind of plot what this is the smoothing spline with 16 degrees of freedom. So again, we kind of talked about if you didn't put a whole lot of restrictions on that arbitrary function g, it can end up being quite wiggly, whereas you know, maybe it makes sense to use cross-validation to try to pick how many degrees of freedom to use. And so in this case, if I fit the blue line, you can see it's a little bit less wiggly in terms of our fit here. Okay, so it's a little bit smoother. I don't know, maybe I'll just do them separately. So that's one, and then the other. So that's with about 7 degrees of freedom, and then this is with 16. So you can see the difference between having lots of degrees of, more degrees of freedom and fewer degrees of freedom. Okay, and then you can Okay, so these are just some of the differences in terms of the different spline functions that R has. Okay. All right, and lastly, if we wanted to fit, here I've done some Lois regression as well for local regression. If we fit using the function Lois, okay, you can have a span at 0.2 or span 0.5, and that's going to kind of determine how wiggly it is. So span 0.2 means use a small window to kind of average the values. So you're going to have more wiggle. When you increase it to have span 0.5, it says use a wider window of values. Okay, so again, you have wiggle, more wiggle versus less wiggle, and that's what we have here when we look at Lois regression. Okay, so all of these are basically, we're just having different functions create different wiggly lines at some degree here. Okay, now which one's the best? It's hard to say. There's not really like a clear explanation that says, Lois is more advantageous than a smoothing spline, which is better or not better than a basis spline or something like that. I think again, the idea here with these generalized additive models is that you are giving up having that functional relationship to have kind of this mostly smooth line that may introduce extra wiggle or not, and I think you kind of just have to eyeball it and say, you know what, based on my experience, it makes sense to use the smoother line. Okay, or perhaps you want to have more the ability to have more wiggle in your fit, for some reason, one or another. All right, so it takes usually some. You don't generally look at the knowledge at the data completely devoid of context, but you'd say, all right, does it make sense that overall, if we look at the relationship between wage and age, does it make sense that there's a bump and a dip right around here in the thing? And as far as ages, maybe that probably doesn't make sense. But then maybe there is something, there is like a real phenomenon that because of your knowledge of the field, you want to say this makes sense, right? Maybe there was a law change in a certain year, and so and that shift for a particular year does appear in the data, right? And if you weren't aware of that, you might see this kind of wiggle right here, and you'd say, well, that doesn't make sense. I'm going to go for the smooth one, right? But then if you are aware of, you have a subject matter expertise in this thing, and you say, well, you know what, that makes sense because in 2012 they introduced a law and this and this and this happened, and you include you allow for your model to have a little extra wiggle, then you can clearly show that and say, maybe in the grand scheme of things it's not that big of a change, but it's enough to show up on the thing there. Okay, all right, so all of these things we've been fitting using linear model between wage and some kind of spline, right? With a generalized additive model, okay, we can do it a few ways, right? We can do our first GAM is just going to be a linear model between wage and a couple natural splines in education or something like this. Education is a a factor. It's a categorical variable, so we're not going to throw it into splines here. Or you can use library gam and say, you know, we want to predict wage as a function of, and then we throw these things into splines. Okay, so we can do that, and we have different things, and here we're going to plot kind of 3 models, and one we'll plot. This is our using the gam function, seeing the relationship between wage, year, age, and education, and it produces this this thing. Okay, and this shows the relationship between kind of year and spline, age and year and the wage, age and the wage, and education and the wage. And so what we see, this is kind of the, maybe this is a little bit exaggerated because it takes up the whole vertical screen, but this is what we see, right? As age goes up, the wages go up, and then they kind of level off, and then they decline after retirement age. Whereas as far as wages go, you know, depending on the year when the data was collected, it seems that as the years went by, the wages went up, except, I don't know, between 2006 and 2007 there was kind of a dip in the wage information that we collected, and so on and so forth. Okay, and so we can see overall the relationship that these different variables have with wage, and they're none of them are linear relationships, and they're not even polynomial relationships, but this gives us kind of shows us the relationship that each of these variables have between each of these variables and the wage. And education, you know, as education level increases, the wage increases, right? That's what we would expect. That's why you guys are going to school, I'm assuming, and so that's what we see here. Okay, so that's using the function gam. Okay, and we can if you plot the results of gam, that's what you get. Whereas over here, this is just the result of a linear model. Gam1 here is the output of a linear model, so we can use the function plot.gam. Okay, this is the gam method. So we're using the method that produced this plot on the output of a linear model. Okay, so normally plot on a linear model produces like a sequence of kind of residual plots and things like that. And we can just say, you know what, I want the gam plot for a linear model. Okay, and this is what we get. And so this, with the gam, we fit natural splines, and so we get this is kind of what our natural splines look like. So something similar, there's a little bit of difference between the gam splines and the natural splines, but overall very similar. Okay, and you know, we can say, well, maybe year is not that big of a deal. Let's just look at age and education, and so these are other possible models. Okay, so this is looking at age and education, and then over here gam M2 is looking at year, age, and education, and we can perform an ANOVA between these things here. So gam1 is looking at age and education only. Gam M2 is looking at a linear relationship between year, age, and education, and then gam3 is a spline of year, spline of age, and education. Okay, and so we can see, you know, what's the difference between these 3 models, and, you know, does it make sense to have one model over the other, right? So if we look only at age and education, and we go to the next model, year, age, and a linear relationship between year, age, and education, it seems like that difference is significant. Whereas moving up from a linear relationship between year, age, and education, and a splined year, splined age, and education, that difference is not significant. So maybe it just makes sense to just leave the relationship between year and wage as a linear thing. So, you know, we see a dip in the spline, but was that significant? You know, according to the ANOVA analysis of variance here, it may not have been when we're comparing comparing models here. So if we look at you know, our predictions here, and we do this, did this. Okay, so something. Let's see. All right. Well, maybe I might not have the function here to plot that, but yeah. So this is I don't know. In summary, this is a generalized additive model. We have we lose the nice explanatory ability of a multiple linear regression model where you have a clear relationship between the predictor and the output y, in that you say as x2 goes up, we predict y goes up by this coefficient. But what you lose in that simple interpretability, you gain flexibility in terms of what the shape of the relationship that can exist between x and y. And the interpretability is not completely lost, in that when we look at something like this, we can still visually see the relationship that a particular predictor has with the output y. Okay, so you might not have a nice linear or polynomial function there, but you still have a visual representation, which is still very often useful in terms of interpretation there. Okay, we'll end here for today. I will post up your homework, homework 2, and then yeah, we'll next week we won't have a midterm. We'll just get into kind of logistic regression and some classification stuff there. Okay.